Hello and welcome to the first wireless product design cycle webinar. My name is Geoff Schulteis. I'm the antenna application specialist at Antenova. Let's get started. First thing to consider during the initial design cycle phase is the required bands of operation. Attention to the bands of operation covered by the radio module must be considered in order to understand the frequency requirements of the antenna, which will dictate the minimum size of the PCB and the overall device size. Carrier bands of operation, radiation limits, and geographic regions will dictate device size as well. In the US, the carriers have bands that go down to 600 megahertz, requiring ground plane lengths of greater than 130 millimeters for the device to work properly. Antenna physics by nature will dictate the size necessary for proper operation. Sacrifice in performance for device size will limit your antenna type, such as their flexible printed circuits versus surface mounts versus trace antennas. Smaller device ground planes will hamper the use of lower frequencies on board antennas and dictate the use of higher frequency bands while limiting the coverage of those lower frequency bands for certain types of antennas. So the higher frequency that you have to cover will allow for smaller devices, such as Bluetooth and Wi-Fi, that will allow for smaller board sizes because they're higher frequencies. So project planning practices ahead of product development tend to speed up time to market and reduce the back-end redesign. So let's talk about the different types of antennas you can integrate into your product. Antenova has had great success with surface mount designed antennas integrating into many different device platforms. The great thing about the surface mount antennas is you can use the pick and place system in order to populate these antennas onto your printed circuit board. That tends to speed up the manufacturing process and lower your manpower costs. Another great thing about it is that they're lower profile, so you can fit these in devices that are fairly slim. They are ground plane reliant, so in order to have a balanced system, you do need to have the proper ground plane length, like I mentioned before. For the lower frequencies, you do need to have a longer PCB in order for the antenna to perform at its optimum. The smaller the ground plane gets, you do sacrifice performance. The next antenna type I'd like to go over is the blade antenna. Blade antenna is used to shorten the overall device length when your device needs to be small, such as like the OBD or onboard diagnostic devices. These blade style antennas require the interaction of a pogo pin or something to contact between your main PCB and some pad landing points on the blade style antenna. Those can be added to your design by using pogo pins, or if you need something a little more robust, you can solder header pins to through-hole vias on your board and then to the antenna, or use a C-clip soldered to the main board and touching on landing pads on the antenna itself. Flexible printed circuits, or FPC antennas, are copper traces that are printed on a mylar tape. This tape can be used to stick the antenna on the inside of your chassis and allow the antenna to get away from the printed circuit board. That way they operate more efficiently. This allows for your printed circuit board to be significantly smaller. However, in order to achieve the lower frequencies, you still have to have a longer antenna, which tends to make the FPCs a little bit longer. So it's kind of a trade-off. With the FPC type antennas, you feed them through a coaxial cable that attaches to your radio via a U.FL or IPEX connector. And by using the flexible printed circuits, you can make them smaller, but what happens is the currents tend to run down the coax, and therefore the coax becomes part of the antenna or the counterpoise. In doing so, you have to be very careful of how you route that coax cable, because if it comes close to ground or comes close to some noisy components on your printed circuit board, you'll find that it'll act as an antenna picking up the noise from your board instead of operating as the antenna for your radio. And that noise feeding into your receiver front end will degrade your overall radio performance. These antennas also tend to be a little hands-on when you're manufacturing with them. In saying that, what I mean is that somebody has to stick it to either a carrier or the inside of your device. So that in itself takes time, and it also allows for some irrepeatability or some difficulties in repetitiously placing the antennas in your device. One thing you can do to overcome that is to put pins inside your housing or on a carrier so that those pins align with holes on your flexible printed circuit antenna, and you can have a little bit of repeatability. The last antenna I'd like to cover are the terminal type antennas. These mount to the outside of your device and typically have the best performance. They attach via SMA connectors that stick out of your chassis, or they have cables that will run inside your chassis and allow for connection via a UDOT-FL or IPEX connector. These antennas are used in critical communication systems such as medical devices or fire, anything that's mission critical. So the efficiency on these antennas tend to be a lot better because you can get them away from your device, the ground plane, or any other metal parts of your device that tend to cause issues with the antenna performance. They are also not ground plane reliant because they have a balanced antenna structure inside of them, and therefore you can mount them pretty much anywhere on your device without having them be detuned by a smaller ground plane. The last thing to consider during your design cycle are the main challenges of wireless design. Consideration for the antenna placement should be the first priority and the top priority. Placement of the antenna inside the device should not be near metallic objects such as Ethernet connectors, USB-C connectors, battery supply lines, data lines, LEDs, or the LCD of your device. All of these generate noise, and the antenna can and more than likely will pick up that noise over the signal that's the desired signal that you're trying to receive. Follow the antenna vendor's guidelines from the outset of the project. Once you determine the type of antenna you will use, follow the guidelines listed in the manufacturer's data sheets for ground clearance and ground length required. Antenna placement is also something to consider. The printed circuit boards can get pretty densely populated, so certain antennas can function better along the long edge of the PCB. Others will like to take up the end of the short length of your PCB, and others function fairly well near the corner of your device. So the antenna position is critical, but can be manipulated. Be sure to clear all metal objects, including on some of the surface mount antennas, the copper that is running through the board layers. Some antennas need to have that areas cleared out. We call that a keep out, and allows for the antenna to operate properly when it's mounted to the surface of your printed circuit board. Other things to consider are not to run power supply lines or data lines underneath the antenna, as this will cause the antenna to be detuned and have a loss of energy, radiated energy, and also could possibly pick up noise from whatever circuit is supplying those traces. So be sure to consider this as priority, not running parallel lines to your RF feed trace or running data lines underneath your antenna. During the architectural layout process, you're going to be moving things around on your printed circuit board, including the antenna, to optimize where things are inside your device. One thing I'd like to mention is something that's not always taken into consideration, which is the plastic housing that your device is integrated into. If you've chosen the flexible printed circuit antenna, then your antenna is going to be stuck to the inside of that housing. And the material that you've chosen can influence the performance of that antenna. I shouldn't have to mention, but I will, that placing the flexible printed circuit on antenna on a metal housing is going to impact the antenna in such a way where the antenna will more than likely not work. So please avoid all metal housings. If you have to have a robust housing that requires some thickness to it, take that into consideration that thicker chassis or chassis made of glass-filled substances will tend to have a dampening effect on the antenna, and you may have some reduced performance. Embedded antennas work a couple different ways. There are antennas that require a ground clearance area underneath the antenna to operate properly, and there are also surface mount antennas that will work on a ground plane where you don't have to clear the copper layers out underneath the antenna. The difference in performance of these two antennas is that the ground clearance antenna will operate in a more omnidirectional or kind of a donut type radiation pattern, whereas the on-ground antennas, they tend to have a little bit of shadowing caused by the ground plane underneath the antenna. Also, you want to consider the different types of antennas you choose, such as the dipole versus the monopole antennas. Dipole antennas are more balanced and they do not require a ground plane to be attached in such a way where the antenna is reliant on the size of the ground plane, whereas the monopole is going to require that the counterpoise or the other side of that monopole antenna is your ground plane, and it's going to be necessary to design a longer ground plane in order to hit the lower frequencies. Inverted F antennas versus planar inverted F antennas versus magnetic loop antennas all work well next to the body, so using them in wearable devices is typically better than a dipole versus monopole. The difference between an inverted F antenna and a planar inverted F antenna is that the planar inverted F antenna is perpendicular to the ground plane, similar to a blade style antenna. Continuing on the architectural layout, you are currently trying to enhance your electrical performance within the smallest package possible. Something to consider are the carriers that you're looking to certify your device with. Some carriers out there offer small device requirements that are less stringent than the other carriers. One other thing to keep in mind is the stability and reliability of your antenna installation during your manufacturing process. Pick-and-place systems work faster and are set up for higher volume manufacturing than hand-placed antennas such as the FPC antenna. You also want to consider to place your radio near the antenna, which will reduce the length of your antenna feed trace and cut the losses that longer traces with bends in them can cause between your radio and your antenna. You want to try to avoid all loss at all cost. Also, switching power supplies and digital lines, I mentioned this before, should be routed away from the antenna area. Moving to the board design, you want to consider the wireless integration for noise rejection. One of the best ways to route a trace from a radio to your antenna is using a grounded coplanar waveguide antenna feed system. What this does is it uses ground on either side of the feed trace along with ground underneath the trace and vias stitched along connecting the two layers of ground above and below the trace to create a waveguide. And the reason for this is that it improves the impedance. It gives you the ability to tune the impedance using that trace. And it also keeps a lot of the noise from coupling to the trace. So you want to also consider laying out your digital components on a separate digital layer. And anytime a trace has to come up to the surface, you want to apply bypassing capacitors to those traces so that they don't tend to radiate. Choosing a 2-layer, 4-layer, 6-layer, or even an 8-layer board will be beneficial in the choice that you do make. A 2-layer board tends to be broken up by the traces that run up and down the board from one component to another, and they slice through the ground layers, so you end up having a non-contiguous ground plane to offer to the antenna. This will end up having the antenna see an electrically short ground plane due to the breaks in the ground plane. So choosing a 4-layer or even a 6-layer board where you can have a ground layer on the top and bottom of the printed circuit board is beneficial. And the reason why is because it offers a longer contiguous ground plane, not broken up by traces running through it, and allows the antenna to see a magnetically straight ground plane. Following the design guidance for the ground clearance and the keep out areas for the antenna is also very important. These stringent outlines are to help with the tuning of the antenna as well as the isolation from noise and other antennas. Now that you're done with the board layout, you're going to go through the Gerber review. This is reviewing all the different layers of your printed circuit board to make sure everything's routed properly. You want to make sure that the digital lines running to your LEDs or data lines to your memory, Ethernet or USB lines never run near the antenna because they produce noise and that could couple into the antenna. Noisy signals on the surface layers from data lines popping up and running along the surface of your printed circuit board can radiate into free space as an antenna. So you want to make sure that you bypass those traces running along the surface layers with capacitors to shunt that noise to ground. Antenna pad size is necessary to check to make sure that you are following the guidelines of the data sheet, and so that your antenna has the ability to hang on to your printed circuit board. At this point, you can consider potting or gluing the antenna to the printed circuit board if your device has higher vibration and drop standards. You want to check to make sure your antenna placement is within a certain distance from your plastic housing so that your housing doesn't hit the antenna and knock it off. You also want to make sure that your ground plane is one solid ground plane for your antenna to operate against. Try not to run data lines near the antenna trace parallel to that antenna feed trace, because parallel lines will couple and you will get noise going into your receiver and degrade the performance. We always recommend a matching circuit to be applied to the antenna feed trace to compensate for any times that the antenna is mistuned by, say, the glue that holds the antenna down, or a thicker chassis, or metal components that are necessary to be close to the antenna. The matching topology is usually a pi network, which is a series shunt configuration that we found offers the best topology for tuning the antenna. If it's necessary to have EMI shielding close to the antenna, we recommend that you keep it as low as possible. A 3mm shield will have some influence on the antenna, but it will not be as significant as a 5mm shield. You also want to design for coexistence, where you have more than one antenna on the board. Say you have a GPS antenna and a Wi-Fi antenna and an LTE antenna, or a Bluetooth antenna operating with a Wi-Fi antenna. Those antennas will resonate in similar bands, and so the energy transmitted by one antenna could be picked up by another antenna. So you want to make sure that you separate those antennas with some space, and also rotate them 90 degrees from each other so that they are orthogonally opposite of each other and their patterns, the radiation patterns, do not couple. Now that you're done with the Gerber review, you're going to send those files out to a board manufacturer. Once the board is manufactured and sent back to you, you're going to want to make sure that your return loss for the antenna is covering the bands that are necessary to meet your carrier requirements. In order to measure the performance of the antenna, you want to have a qualified lab measure the passive efficiency of your antenna in an anechoic chamber. Once you have that efficiency, you can also have them measure your envelope correlation coefficient if you have more than one antenna operating in the same frequencies, such as dual MIMO LTE antennas. Envelope correlation coefficient, or ECC, is a measure of how different those two antenna radiation patterns are to take on the full benefit of MIMO performance. You want to also manage the interference problem between the two antennas. If you have an isolation issue where the antennas have too much correlation or they crosstalk to each other, at this point you're going to want to go through a redesign phase and move the antennas away from each other a little bit more, or change their rotation from one another to make sure that they have the proper isolation. You can also check to see if you have any EMI issues that will pollute the receive signal and your receive chain by sniffing the board while it's transmitting and finding out, if using a spectrum analyzer, if any of the traces or components on your board are radiating signals in the bands of interest. This also helps to mitigate FCC issues when you get to the FCC lab for certification, or PTCRB. At this point, you also want to check your power consumption. Make sure your traces are short and that there are no bends or very few bends in the trace as possible. The more signal loss or trace loss that you have, the more battery you're going to require, or it's going to use, in order to transmit, and you want to have as efficient a system as possible. How to pre-test an embedded antenna. You can't always go with the module supplier's suggested recommendations because sometimes they don't fit. So you want to characterize your return loss in the device and make sure that it is set accurately so that you get all the power transferred from the radio to the antenna without any loss, or as little loss as possible. Once you start getting closer to your design verification test builds, you're going to want to pay close attention to the PCB material you have selected. The DVT boards are small production run boards, and sometimes they use a different stack up or a different material in the quick turn boards versus the production material. So you want to make sure that the PCB thickness and your stack profile are very similar, because your impedance of your grounded coplanar waveguide is relying on those tolerances to stay the same in order to be tuned properly to the proper impedance. You also want to make sure that when the solder mask is created, you get enough solder on the pads for the antenna to hold it to the board. Sometimes the solder mask openings are not wide enough and you don't get enough solder, or you don't get enough flow of the solder to hold the antenna down. You want to also verify that you're working with the final matching components and they're on your BOM, so that when you do go to the production runs, you're not caught on an old rev of tuning components. You also want to make sure that you have manufacturing instructions in place if you're using an FPC antenna, to show clear guidance on where and how to mount that flexible printed circuit to your housing. Also consider your test costs of the certifications for FCC or PTCRB, or your carrier certifications. Those are going to be coming close to all of the, or 40% of the manufacturing costs in some cases. Verifying that your antenna is connected to your board is significant. It's pretty important to make sure that the antenna is making connection to your radio. You want to make sure that there's some way, a test jig or whatnot, to try to ensure that the antenna is making connection. Also, you want to, during drop tests, have a way to verify that the device is still working. Typically that's in a test jig, and you turn the transmitter on and make sure that the device is still transmitting. Moving to mass production is sometimes a stressful situation. Making sure that you've selected the right antenna for the product is critical in having a successful development and a successful launch. Surface mount antennas are cheaper for mass production, but if you're working with lower quantities, hand-assembled FPCs can work well for you. Using production processes such as locating pins or plastic carriers for FPCs can create designed-in repeatability during manufacturing. Using the correct antenna for production is not always a straightforward situation. Coming up more often as more companies outsource production, things like exotic materials and like laser direct structuring or LDS antennas can create stumbling blocks and extend the manufacturing process for certification. Anytime something goes wrong, you have to take a step back, and that adds delay. So thank you for joining me. I appreciate the time you've taken to discover the process of designing wireless abilities into your product.